I'm Antonio Sala. In this video we are going to discuss how to extend the geometrical interpretation of the new gap metric from Vinicomp to a complex and multivariate case. No proofs, just a very fast and informal account of some ideas. The basic idea on all this is that if we have a controller that achieves some normalized coprime factor uncertainty margin, then it tolerates some delta and delta D. However, if P1 is 8 and P2 is 8.5, then how do we compute this numerator and denominator uncertainty? This seems difficult to compute at first glance, but we gave a geometric interpretation in the real case in previous videos. So here we will recall that interpretation and extend it to a complex case and also to the matrix multivariable general situation, but again informally and without any proof. If you wish to delve into the nitty-gritty formal details, just read Vinicomp's PhD thesis or the book down there for full proofs. If we recall the real case, any number can be expressed as an infinitude of pairs numerator and denominator so that the ratio is, say, P1 or P2. So in the numerator-denominator graph space, the blue line is a line with slope P1 and the normalized factorization is the green star, so that the minimum distance to the red line is the sinus of the angle between the lines. Here we have it. This is the new gap. We had an alternate formulation as a caudal distance in the stereographic projection. In particular, it can be proved that if I take this circumference of half the diameter of the original one, the distance between the pink points, the length of this chord, is also the sinus of the angle. We also had some formulae for the sine of that angle if I had the normalized description of P1 and P2, or well, as such normalized description is this thing. If I replace these descriptions in here, then I get this expression. So, once we have this formulae and these two geometric interpretations, now we need to address the case in which P1 and P2 are complex numbers because they are the frequency response of some P1 of S, P2 of S. Well, the interpretation is basically the same, caudal distance. It's the same graph here, but okay, now we think instead of a circle on a sphere, and instead of having real stuff here, we extend so that what it's down there, it's a plane. In that way, we get this representation. In the complex plane, this sphere is called Riemann sphere in complex analysis. But okay, the interpretation of the new gap is again the caudal distance, the distance between the 2 points in this stereographic projection on a sphere instead of on a circle. There is also an angular sine interpretation. You can imagine it with a larger sphere in this case and a plane here, but we omit it for brevity. So, once we have the new geometric interpretation, let's go with the generalization of these formulae. If there were a complex number, it's just copying the same, but P1 being complex, well, instead of the square of a real number, we will put here the modulus of a complex number, so we would replace this thing by P1 conjugate times P1. This would be the square of its modulus, and if there are transfer function matrices, then we get the following general stuff: P1 squared real case P1 conjugate P1 complex case, then if it's a transfer function matrix, we need the conjugate transpose matrix. If I have a dynamic system, then if I transpose it and change sign of the Laplace variable, then its frequency response, it's pre-transposed at minus j omega, which is the conjugate of the frequency response. So this is a clever, widely used trick in order to manipulate magnitudes and power spectral densities of multivariable plants. But okay, the details are out of the scope of this discussion. The issue is that if we do the matrix version of this formula at every frequency and we compute the maximum of it, this infinity norm, well, then we get this expression whose formal proof is in Winnicombe's seminal references. Last, the generalization of this expression, well, or the change sign, because we are just taking the absolute value in the real case. Well, in the complex multivariable case, if we get this factorization of P1 and this one of P2, one of them is the left coprime factorization, another one is the right coprime factorization, because in matrices the order of the things is important. Again, details are not in the scope of this video. Well, the issue is that we get this formula frequency by frequency and its peak. Then that defines this psi function. It's the same, and when we restrict to a real case, we get the formula for which we gave a full explanation in another video. At the end, this psi allows us to define the new gap as this psi if some technical conditions over Nyquist diagram winding numbers related to unstable poles and zeros of P1, P2, etc. Okay, I mean, these conditions arise from the need of delta n or delta d to be stable to apply a small gain, or some relaxations of that small gain condition based on Nyquist. But okay, read Winnicombe's book for details. The issue is that, okay, if those technical conditions hold, then this is the new gap, psi, and otherwise the gap is 1. The maximum value of the maximum distance, the maximum sinus is 1, so it will be impossible to design a controller with margin 1. In the case the gap is not 1, it can be proved that if the coprime factor uncertainty margin with a given controller and P1 is greater than this new gap, then P2 is also robustly stabilized by K. This is the important result in practice. As I said, these technical conditions are key for mathematical correctness of all this discussion, but they are not really intuitive and important in robust control practice. I mean, our goal will be designing controllers with a good enough margin, so the greater the margin, the largest the ball of uncertainty in this new gap we will be able to tolerate. And what's the meaning of this new gap? Well, the idea is that when P1 and P2 are close to 0, well, basically this distance is the same as the difference, the additive uncertainty on P1, let's say, but the same distance at a higher angle, the same new gap corresponds to a much larger additive uncertainty difference between P1 and P2. So the new gap between point 1 and point 2 is roughly the same as the new gap between 10 and 700. So this is good in intuition. It sort of indicates that a controller with a reasonable NCF margin will tolerate a large amount of uncertainty when the plant has high gain and the trick is not amplifying too much low gain region of the plant. Okay, we'll discuss that in more detail in a forthcoming video. In here, let's conclude. In a real case, the new gap can be interpreted as a sine or as a caudal distance in stereographic projection. The same interpretation can be extended to the complex plane and the 3D stereographic projection, and, well, with suitable graph topologies and Hilbert spaces stuff, it can be extended to these formulas that, okay, MATLAB computes that new gap with this command, the second output, but as usual, weights are needed in many cases to give a meaningful interpretation in applications, and grosso modo, new gap shrinks uncertainty at large amplitudes, which is good. Of course, apart from frequency response matrices, the new gap can be computed from ABCD matrices of P1 and P2, and MATLAB takes care of these stability-related technical conditions. So we finish with this. Thanks for watching.